Welcome to Fixed and Split Limits Analysis in SPC, a VA Quality Scholars Methods and Analysis Learning module. I'm Dr. Brant Oliver, a healthcare improvement scientist at Dartmouth-Hitchcock Health, a large healthcare system in New Hampshire. I'm also an associate professor in the departments of Community and Family Medicine, Psychiatry, and the Dartmouth Institute at the Geisel School of Medicine at Dartmouth in New Hampshire, and serve as the lead QI Methods and Analysis faculty for the Department of Veterans Affairs National Quality Scholars Fellowship Program. This learning module was adapted in collaboration with VAC's measurement and analysis faculty colleagues, Drs. Molly Horstman and Susie Miltner, using original content developed by the faculty of the PH 126 Measurement and Statistical Analysis for Quality Improvement course in the MPH program at the Dartmouth Institute and used with permission. Fixed and split limits analyses are advanced analytic operations that can be conducted to modify standard statistical process control, or SPC, analyses to provide additional assessment capabilities. Fixed and split limit analyses are not always required, and in many cases a standard SPC analysis will serve very well to assess variation and inform improvement. However, there are some cases in which fixed and split limit analyses can be very useful. This algorithm can help guide your thinking when considering whether to conduct fixed or split limits analyses in SPC. First and foremost, start with an appropriate and comprehensively interpreted standard SPC analysis for the data you are assessing, including the mean, range or precision, the type of variation, common or special cause, and a determination of whether or not the process is in statistical control. In the algorithm, this is shown in the blue box. If you conduct fixed or split limits analyses, you will make changes to this standard SPC analysis to create them. Next, let's consider the option in the red box, Fixed Limits Analysis. A fixed limits analysis can be helpful when you wish to increase the degree of sensitivity to detect a special cause signal or non-random variation when you are testing the effect of a planned change or intervention or a known exposure versus an established, stable, and reliable baseline state to assess whether the change made results in an improvement. This is achieved by recalculating the center line or mean and control limits using only the observations from a reliable baseline period prior to a planned exposure or intervention. All future points observed after the baseline will be plotted against this new center line and control limits, which will remain fixed and unaffected by the new observations. There are three considerations for fixed limits analysis. First, do I have a stable baseline? Second, do I have a known exposure? And third, do I need to maximize sensitivity to detect special cause variation compared to a set baseline? If the answers to these three questions are yes, consider a fixed limits analysis. Next, let's consider the option in the green box, Split Limits Analysis. Unlike fixed limits, which is designed to increase sensitivity to detect special cause variation signals, a split limits analysis is used after a change in a process has occurred to determine the characteristics of the new process, such as the new mean, the new range or precision, and the new variation pattern, and whether the new process or change in performance is sustained. There are two different approaches taken to determine when and where to conduct a split limits analysis: the pragmatist perspective and the empiricist perspective. The pragmatist perspective relies on actual knowledge of the context under study, suggesting that a substantial change in the process has occurred, such as a dramatic change in practice patterns or a safety incident. The empiricist perspective relies only on the statistical properties of the data under study. In this approach, detection of a sustained special cause signal, such as a shift or trend, is required prior to splitting the analysis. In both approaches, the split is typically made at the beginning of the event. There are three considerations for split limits analysis. First, is there a sustained special cause signal identified? Second, is there a context knowledge suggesting the presence of one or more substantial process changes? And three, do I want or need to prioritize the assessment of new system characteristics and sustainability? Finally, creating split and fixed limits analyses is much easier than the reasoning required to assess whether or not to conduct them. Many SPC software packages such as QI Macros, SPC Excel, Minitab, and others can conduct fixed and split limits analyses at the press of a few buttons. Now we will use an actual example to demonstrate fixed and split limits analyses from a case study published in the New England Journal of Medicine concerning a significant healthcare safety incident. In this example, the authors report an outbreak of Pseudomonas infections following the introduction of new flexible bronchoscopes in June of 2001, resulting in a recall of the scopes in December of that year and a withdrawal of the scopes in February of 2002, as shown by the three red arrows. SPC analyses were not used in the original report, but could be applied here in an attempt to increase sensitivity of detection of non-random or special cause variation in Pseudomonas events, and perhaps could have triggered an earlier recall of the scopes and result in reduced Pseudomonas morbidity. On the left-hand side is monthly proportions data of the proportion of patients receiving flexible bronchoscopy procedures who contracted Pseudomonas infections. On the right is a standard proportions chart, or P-chart, of the proportion of patients infected by month generated using QI Macros software. Let's orient now to the timeline previously established. The outbreak of Pseudomonas infections followed the introduction of new flexible bronchoscopes in June, resulting in a recall of the scopes in December and a withdrawal of the scopes in February, as shown by the three red arrows. Next, as a review of SPC basics and as a necessary and required first step prior to considering fixed or split limits analyses, let's conduct a thorough standard interpretation using the Big Three method, which is 1. The mean, 2. Maximum range of variation or precision, and 3. The type of variation, common or special cause. The mean Pseudomonas infection rate, center line, is approximately 17%, which corresponds to the blue center line and is also shown in the blue circle. The maximum range or precision is calculated by subtracting the highest and lowest points, which are indicated by the green circles. In this case, the maximum value is approximately 50% and the minimum value is approximately 3%. So the range is the difference between the two, or 50 minus 3, which equals 47%. This is a rather wide range of variation indicating very poor precision. Remember that as range increases, precision decreases, and vice versa. Finally, assessment for basic special cause signals, including shifts, trends, or points outside of the 3 sigma control limits, finds a special cause variation pattern based on the signals identified in the red boxes. This includes 2 large shifts of at least 8 consecutive points above or below the center line and a number of points outside of the control limits, each of which is a separate special cause signal. No trend of 6 or more consecutively increasing or decreasing points is present. The presence of one or more special cause signals indicates a special cause variation pattern, in this case suggesting a non-random upward variation in infection rate following the introduction of the new scopes. Based on this analysis, the recall could have been issued in October based on the first special cause signal detected, as shown by the green square and arrow, 2 months prior to the actual recall in December of the same year. Note that there are additional special cause signals that can be assessed and are not assessed here for sake of simplicity, including 1 and 2 sigma signals. Also note that there are many different special cause detection criteria, including the Institute for Healthcare Improvement, or IHI, Westgard, Duran, and many others, each of which may be preferred in specific situations. In this module, we will use the IHI detection rules, as these are commonly used in healthcare improvement applications, and also because the IHI rules are used for the measurement and analysis curriculum in the VA National Quality Scholars Fellowship Program. Now that we have completed a standard SPC analysis, let's consider a fixed limits analysis. Fixed limits sets or fixes the center line at an established baseline or pre-exposure level. It requires a baseline that is in statistical control and known chronology of baseline and exposure or intervention periods. Fixed limits analysis can increase sensitivity to detect special cause variation post-exposure compared to a set baseline, and can be used in surveillance, improvement and improvement science, safety and reliability situations. In the picture on the right, 2 run charts are shown. The one on the left has a median or center line calculated using all of the values observed. The one on the right has recalculated the center line to create a fixed limits analysis using the values from an established baseline period, shown in the red box on the left. The fixed limits analysis, which raises the median value based on the values in the red box, increases sensitivity to detect the downward shift shown in the red circle following the baseline period. As discussed previously, one of the main criteria required to be present prior to conducting a fixed limits analysis is a stable baseline. A stable or reliable baseline must have 3 characteristics. First, it must have at least 12 to 15 observations at minimum. 20 or more is ideal. Second, the observation or baseline period must be free of a known exposure or intervention. And third, the process must be in statistical control or evidence common cause variation. Now let's apply these criteria to the case study, pulling forward the standard SPC analysis from previous. The baseline period here includes observations prior to the introduction of the new scopes. This is shown in the red box. The introduction of the new scopes is shown by the red arrow. Let's examine the area in the red box to see if we have adequate power or acceptable type 2 error risk based on the number of observations present. In this case, there are barely enough values to meet criteria, 12 in total. Remember that the criteria is 12 to 15, with 20 or more being ideal. Second, let's examine to see if we can reasonably conclude that the intervention or exposure is not present during the baseline period shown in the red box. Because the exposure, the new scopes, shown by the red arrow occurred after the baseline period, we can reasonably conclude that the baseline period is free of the exposure effect. Third, we need to examine the baseline period to see if it is in statistical control. Remember that in SPC, to achieve statistical control, a process must be free of special cause signals, which means that it demonstrates a common cause variation pattern. The display which has just appeared is a new p-chart created using only the baseline data points in the red box. A quick interpretation of this analysis reveals an absence of special cause signals, meaning that there is a common cause variation pattern present. This suggests that the baseline is in statistical control, which means that the centerline value, the mean of approximately 10%, shown in the green circle, has acceptable statistical stability to be used as a reliable baseline value to compare against a future exposure or intervention. Now that we have assessed the baseline, let's revisit our algorithm to assess whether we want to conduct the fixed limits analysis. To review, our criteria include, first, do I have a stable baseline? The answer to that is yes. We have previously established that we have a stable baseline infection rate of 10%. Second, do I have a known exposure? The answer to that is yes as well. We have previously established that we have a known exposure, the introduction of the new scopes, which occurred after the baseline period. And finally, do I need to maximize sensitivity to detect special cause variation compared to a set baseline? Arguably, yes to this as well. It could be argued that in this case, where patient safety is involved and surveillance of infection rates post-introduction of a new exposure is required, that there is need to maximize sensitivity to detect special cause variation compared to the established baseline in order to inform the most prompt action possible should a non-random or special cause variation in infections be detected after introduction of the new scopes. Based on the criteria above, this situation appears to meet full criteria to conduct a fixed limits analysis. Here is a fixed limits analysis of the original dataset created using QI macro software using the new center line and control limits based off of the baseline period shown in the red box. Note that the new center line is the baseline average of approximately 10%. The red arrow shows where the new scopes were introduced in June. Note here that 1 and 2 sigma lines have been added to the display, and a 2 sigma rule special cause signal is detected on the same month that the scopes are introduced, as shown in the green circle. A 2 sigma rule signal is 2 out of 3 consecutive points above the 2 sigma line, which here is shown as a dotted red line. These lines can be turned on and off using the software and can help to detect 1 and 2 sigma rule special cause signals. Also note that a second 2 sigma signal appears the month afterwards as well, shown here in a blue circle. Both of these signals indicate non-random or special cause variation with an increase in infection rate following the introduction of the new scopes, and could have prompted action to recall the scopes within a month or two of their introduction, much faster than the original recall, which was in December of that year, nearly 6 months after the scopes were introduced. For comparison, the bottom chart shows the standard SPC analysis. Note that the original centerline mean of approximately 17% is shown. The standard analysis detects a 2 sigma rule signal in September, roughly 3 months after introduction of the scopes in June, not quite as fast as the fixed limits analysis, but still 3 months faster than the original recall date in December. Finally, as shown in the dotted green circle, we have a sustained special cause signal in the fixed limits analysis, which is a shift of 8 or more consecutive points above the mean. Note that in the standard analysis, on the bottom, it falls short of meeting the full 8-point criteria and does not detect the shift. This suggests that the increase in infection rates is sustained for a number of months compared to the pre-exposure baseline of 10%. This finding will also be important when considering a split limits analysis subsequently. At this point, we have now identified a situation via standard and fixed limits SPC analyses in which a change in the process post-introduction of the new scopes occurred, and unfortunately, it is a negative or bad occurrence, namely a non-random increase in infection rates post-introduction of the new scopes, which emerges within the initial months after introduction. These findings could inform prompt action to recall the scopes and thus minimize related infection morbidity much sooner than the original recall. Note that in this case, we are interpreting these analyses retrospectively. In real-time prospective analyses, the standard and fixed limits analyses would be similar as they are more proximal to the end of the baseline period. And over time, they will diverge increasingly as time progresses away from the end of the baseline period, with the fixed limits analysis maintaining a fixed mean and providing increasing sensitivity compared to the standard analysis, which will continue to adjust its mean over time with the addition of each new data point. Now that we have conducted and interpreted a fixed limits analysis, let's consider a split limits analysis. A split limits analysis is considered after a non-random change in a process or performance level has been detected, either pragmatically or empirically. In this case, we can consider split limits based on both perspectives. From a pragmatist perspective, we know from the case history that a fundamental change in the care process occurred with the introduction of new scopes in June. And from an empiricist perspective, we also know from previous that there is a sustained special cause signal identified, a shift of 8 consecutive points above the mean, detected in the fixed limits analysis indicating a sustained increase in infection rates that persists after introduction of the new scopes. Remember that meeting criteria from only one of the two perspectives, pragmatic or empirical, is required to consider split limits analysis, but in this case, the situation meets criteria by both approaches. In the picture on the right is an example of a split limits analysis for needle sticks, with a new mean and control limits calculation beginning at the start of the second process shown by the red arrow. In this case, the split was made based on empirical criteria, based on the identification of a sustained downward shift in needle sticks to the right of the arrow. The result is two process performance analyses, one on the left and one on the right, each with its own mean, range, and type of variation characteristics. Let's discuss the characteristics for split limits analyses shown in the bullets on the left, and then apply them to the case example. Split limits analyses split a single analysis into two or more separate analyses. Each of them have its own interpretation and variation characteristics. Empirical or pragmatic rationale can be applied to justify a split limits analysis, and split limits analyses can be used to assess the characteristics of a new process post-observed special cause variation or fundamental process change, to compare pre versus post-state conditions, and to assess for stability and sustainability of new processes or improvements. Now let's revisit our algorithm, this time with a focus on considering the split limits analysis and consider each criteria in turn. First, is there sustained special cause variation present? The answer to that is yes. We have previously identified a sustained upward shift, a special cause signal, which occurred post-exposure to the new scopes. This satisfies the empirical approach criteria. Second, is there context knowledge suggesting the presence of one or more fundamental process changes? The answer to this is also yes. From the case history, we have previously identified that a fundamental change in the care process occurred, which began with the introduction of the new scopes following a defined and reliable baseline period. This satisfies the pragmatic approach criteria. And finally, do I want or need to prioritize the assessment of new system characteristics and sustainability? Arguably, the answer to this would be yes as well. There would arguably be value in conducting a split limits analysis to add new information to complement the previous standard and fixed limits analyses. Specifically, now that the previous analyses have detected the non-random increase in infection rates post-exposure to the new scopes, it would now be helpful to know the new mean infection rate, the range of variation in that infection rate over time, and whether or not the increased infection rate is sustained, and if so, for how long. Given that all three split limits criteria are met, we will proceed with conducting a split limits analysis. Let's begin with the fixed limits analysis previously conducted. We will carry forward the red arrow showing when the new scopes were introduced, the solid green circle showing the original 2 sigma signal detected in the fixed limits analysis, and the dotted green circle showing the sustained upward shift observed. Note that in this case, we would most likely choose to split the analysis beginning in June of 2001, the month that the scopes were introduced, as shown in the blue circle, which would be recommended by pragmatic criteria, and it is also the beginning of the sustained upward shift in infection rates, shown in the dotted green circle, making it the recommended split point from the empirical perspective. Using QI macro software, a split limits analysis was conducted with the split made between the end of the baseline period in May of 2001 and the beginning of the exposure period in June. Note that the process to the left, the baseline, has a familiar mean of approximately 10% that we saw previously in the fixed limits analysis. On the right, however, we have a much different story. Note that the new mean, shown by the blue center line with the value circled in blue on the right, is 23.6%, more than twice that of the baseline rate of 10%. This is an alarming increase in infection rate compared to the baseline that appears to be sustained for a number of months. The range of variation is also considerably wider on the right than on the left, indicating worsened precision comparatively. Additionally, the presence of special cause signals, shown in the dotted red circles, shows that the new mean infection rate on the right is not sustained over time. The first dotted red circle on the left, evidenced by a 2 sigma rule signal as well as 2 points above the upper control limit, indicates a further non-random increase in the infection rate compared to the existing 23.6% mean. The second dotted red circle, also evidenced by a 2 sigma rule signal and 2 points below the lower control limit, indicates a non-random decrease in the infection rate compared to the existing 23.6% mean. Next, we will add arrows which provide annotation to the split limits analysis and places the new interpretation of the findings in context. The first green arrow on the left shows when the new scopes were introduced in June. The second green arrow in the middle shows when the original recall was issued in December, and the final green arrow on the right shows when the new scopes were withdrawn in February. Finally, adding a blue arrow to the analysis shows how much sooner a decision could have been made to withdraw the scopes based on the fixed limits SBC analysis findings. We will now revisit the algorithm one final time to conclude the module with a brief review, starting with a standard SPC analysis in the blue box. Fixed limits analyses in the red box can be considered when there is a specific interest in maximizing sensitivity to detect special cause variation after a known exposure or intervention is applied compared to a stable baseline state. There are 3 criteria for considering a fixed limits analysis. First, do I have a stable baseline? Second, do I have a known exposure? And third, do I need to maximize sensitivity to detect special cause variation compared to a set baseline? If the answers to these 3 questions are all yes, you can consider a fixed limits analysis. Split limits analyses, shown in the green box, are used to examine the characteristics of a new process once a fundamental change in an existing process is identified, either pragmatically or empirically. There are 3 criteria for considering a split limits analysis. First, is there a sustained special cause variation present, such as the presence of a shift or a trend? Or is there context knowledge suggesting the presence of one or more fundamental changes in the process present? And third, do I want or need to prioritize the assessment of new system characteristics and sustainability? If the answers to these criteria are yes, you can consider a split limits analysis. This simple algorithm can serve as a helpful quick reference guide as you consider fixed and split limits approaches in your SBC analyses. This concludes the learning module introducing fixed and split limits analyses in SPC with application to a published case study. Best wishes for success in applying these principles to your analytic and improvement work.